Chapter 8, question 23, two identical 0.9 kilogram masses are pressed against opposite ends of a light spring of force constant 1.75 newtons per centimeter, compressing the spring by 20 centimeters from its normal length. Find the speed of each mass when it has moved free of the spring on a frictionless horizontal table. So we're given the two masses which are equal to each other, which is 0.9 kilograms. The spring constant is, or the force constant is 1.75 newtons per centimeter, which equals 175 newtons per meter. And the distance that the spring is compressed is 27 centimeters, which equals 0.2 meters. And we know the initial velocities for both A1 and 2 is equal to 0 meters per second, meaning that their initial momentum is the two masses times the velocity, which just equals 0. And by conservation of momentum, P2 must equal P1, which equals 0. So the momentum of each added together, so 0.9 kilograms times velocity 1 plus 0.9 times velocity 2. We can bring one to the other side. Equals 0.9 V2. Those cancel out, so the velocities of both masses are the same once they're propelled from the spring. From there, we will use the equation. So the potential energy of the spring, potential elastic energy of the spring, equals the kinetic energy of mass 1 and 2. We know that the equation for potential elastic energy is 1/2 times the spring force constant times the distance squared. And we know that the kinetic energy for the two masses will just be, since they're the same, it'll just be 2 times 1/2 mass times velocity squared. And those can cancel out. And we want to solve for the final velocity of both of these masses. So we will divide each side by the mass and square root each side. Therefore, the velocity equals the square root of the potential elastic energy, which is 1/2 kx squared divided by the mass. And to plug in for those, we have the square root of 1/2 times 175 times 0.2 squared divided by a mass of 0.9 kilograms. That gives us a speed of 1.97